Video solution for E&M on exam number 1 on problem 1. It says consider two infinitely long wires carrying current I in the same direction at distance 2d apart. Using the Maxwell stress tensor, find the force per unit length of one wire on the other. Assume the wires run parallel to the z-axis so that the xz plane lies symmetrically between them. Only consider the effect of the magnetic fields produced by the current. So we have two wires, distance 2d apart, and running parallel to the z-axis here. Well, if we look at that from a face-on angle and draw a semicircle or a hemisphere around it, this would be the xz plane, and then this would be the hemisphere. If we can figure out the net force on this plane, then that would be the same as the force that we need to figure out for the force per unit length from one wire on the other. We make the argument that because this is symmetrical about this point, that the net force on the hemisphere part is going to be 0. So we only need to worry about the plane. So, disregarding this, we have our standard formula for a wire, magnetic field of a wire, B equals mu naught I enclosed over 2 pi r phi hat. And if we consider a point on the plane, and this comes from there to there, going out, that would be our, this actually would be the radius, so that the magnetic field, poorly drawn, through that point looks like that, and then coming back from the bottom part would it look like that, essentially coming back the other way. Once again, really poorly drawn. But anyway, so if we look at this point right here and consider a right triangle with this angle theta, then cosine of theta would equal, since this is d because they're 2d apart, would equal d over r. And then r would equal d over cosine theta. Now, looking at this point, you're going to end up with one magnetic field pointing down that way, the top one, and then the other one pointing down in that way. So essentially, the x components of these are going to cancel out, and then the y components will add up. So the force on this plane will be in the y direction. So making this substitution for r, the field on the plane would be mu naught I over 2 pi times the distance between them times cosine theta in the y hat, we can call it the negative y hat direction. And then the total, since there's two of them, would just be negative mu naught I over pi d cosine y hat. Right. Then using that, we can figure out, using this for the magnetic field and using this equation for the stress tensor, the electric field components cancel out because the electric field is 0, which means for this equation, S would be 0. So this whole thing would be 0. So the force would be equal to just the integral of t dot dA. Figuring out what Tyy is using this guy, we end up with Tyy equals I over pi d cosine theta quantity squared y hat, and then plugging it into that equation over the area integral, this would become the double integral from 0 to L and negative pi over 2 to pi over 2 of this guy squared cosine squared theta times dl d theta. Evaluating that, you just end up with I squared L over 2 pi d squared, and then dividing by the length, you just end up with, oh, missed a factor of mu naught in here, right, because of this mu naught, so one in there, mu naught, and then that 1 over mu naught at the beginning here cancels one of them, so we're left with 1 mu naught over 2 pi d squared, and then dividing out the length to get the force per unit length. We end up with mu naught I squared over 2 pi d squared. That's in the y hat direction. So we should get just the same thing except with only a single d in the bottom, and I'm not too sure where that other d goes. But that's my solution.